So welcome back everyone. Today we will study solar cell working principle. So solar cells, as we know it, it is made up of semiconductor diodes. And nowadays there are various kind of solar cell designs uh, involving hybrids also. And nowadays people are now developing various semiconducting materials involving direct bandgap semiconductors and all for solar cell also, solar cell applications also. And people are now working on perovskite based solar cell, which is organic and inorganic absorber layer. But the existing technology, that is the one which is being circulated in the market, or the one you usually see in your street light. Also you will have a solar panel and all, and in some houses solar cells, solar panels are mounted. So solar panel basically it consists of one solar panel will consist of uh, around 24 solar cells connected in series. So depending on the dimension of the solar panel, within one panel there can be a number of solar cells which are connected in series. Right. Now, in order to increase the power generated from the solar cells, like in one solar panel, number of solar cells are there and which are connected in series. Another solar panel, large number, around 24 solar cells will be there and they will be connected in series. And let's say each solar cell can give out around, let's say, 10-watt electrical power, and let's say the open circuit voltage is, let's say, 2 volt or something. Now if you add 24 solar cells, if the solar cells are connected in series, so you add 24 multiply with 24, 48 volt. So roughly, for example, this is just an assumption, within one solar panel you might be able to get 48 volt also. Now 40 usually more than one panels, they will be connected in parallel again. So from one panel, so I think what I assumed is a little bit too much. Let's say 0.5 volt is generated by each solar cell, and let's say there are 12 solar cells in one panel. So 0.5 into 12, no, let me say this is 0.5 into 12. This is just an assumption. Okay, so let's say one solar cell can give 0.5 volt, and within one solar panel you have as many as, let's say 24 cells, 24 cells connected in series like this, connected in series, end-to-end connection. So there will be 24 cells connected in series. So the total voltage from one panel will be 24 cells into 0.5 volt. That will be 12 volt. So let us assume that one panel can give 12 volt, and there will be another, let's say, number of panels, each giving 12 volt, 12 volt, 12 volt. And if you connect all these cells in parallel, sorry, all this panel in parallel, if you connect all of this panel in parallel, so the current coming from this 12 volt cell, let's say this is 5 milliampere, 5 milliampere each, 5 milliampere each. So the resultant current after parallel connection will become 15 milliampere. And if you measure the current generated from these three panels, it will be 15 milliampere, and the voltage it gives will be 12 volt. So 12 volt, 15 milliampere power can be extracted from such an arrangement of solar cells. That is, having three solar panel, in one solar panel 24 solar cells are there, and assuming that each solar cell can give out 0.5 volt open circuit voltage. So one panel can give 12 volt, and if you have three panels, then if you connect them in parallel, uh, the total current can be around 15 milliampere, just as an example. So this is how people are actually designing a large solar power station. So in a single solar power station, there will be a number of solar panels. So within solar panels, there will be a number of solar cells. So it may not be 24, it may be more than 24 also, it may be less than 24 also. So depending on the design, you can have a number of solar cells within one panel, and uh, those many number of panels can be connected in parallel to form one solar power station, right? So what we are going to see for today's class is how one single solar cell is constructed, and how it is converting light energy into electrical energy. So the main purpose of a solar cell is conversion of light energy into electrical energy. Light energy, which we receive from the sun daily, it is considered renewable energy, because it it cannot be easily consumed. So every day, like within a circle of 24 hours, we will receive sunlight. So which you cannot like spent up, unlike the fossil fuels. The fossil fuels and all, petroleum, diesel and all, we have certain amount of fossil fuel reserves in the world. So if we do not use those reserve fossil fuels judiciously or economically, uh, one day we will end up using all of the remaining fossil fuels in within the earth. Uh, of course, like fossil fuels also can be renewed, but the time it takes to form sufficient quantity of fossil fuels is like it's too long. So in order to form a certain fossil fuel uh, in a certain area, it takes more than almost 1,000 years and all, right? So more than 1,000 years. So uh, we can consider those fossil fuels as non-renewable, because we can use it up before another like another fossil fuel, another batch of fossil fuel is formed due to the composition of those all those fossils under the earth. So they are considered non-renewable. But however, sunlight and all are considered sunlight and all is considered a renewable energy source, because we are getting it daily, and you cannot say that today I spent too much of solar sunlight, and I will not be getting another sunlight tomorrow. It's not like that. The nuclear fusion reaction in the sun, it is uh, taking place continuously, and we know that, like, there are some uh, like some astronomical phenomena, like solar flare and supernova and other kind of thing. Like a very old star, if like the sun like the other stars, it also has a certain lifespan. So after several billions of years, our sun also will undergo some sort of supernova, and then it will give out large spectrum of light, and then eventually it will die down also. So that will take hopefully another thousands of year. So we do not have to worry about that for now, because the hydrogen fuels in the sun will continue to generate this solar light for a very long years, uh, which will probably be much more than our lifespan. Okay, so therefore we can consider this as our renewable energy source. Now, how is the solar cells designed using semiconductors? That's what we are going to study. How solar energy, light energy can be converted using PN junction into electrical energy. So the design is something like this. Uh, let's say, let us look into this perspective. Let's say this is a PN junction, and here we know that there is a depletion region in the PN junction. This is the junction and this is the depletion region. And in the depletion region, on the inside there is a positive ion formation that we have already talked about. Positive ion. On the P side there will be negative ion formation. And on the inside we have large quantity of free electrons. Large quantity of free electrons. And on the P side, we have large quantity of holes, large concentration of holes. In fact, large concentration of holes due to acceptor atom doping and due to donor atom doping. We have talked about this. Now, the usual forward biasing is if I connect this P-type to plus terminal of the battery and N-type to negative terminal of the battery, electrons from the N side will gain energy from the negative potential here, and as it gains the energy from the negative potential here, those negative energy will give energy to these free electrons, majority free electrons, and the majority free electrons can climb over the potential barrier, and the electron can go from N side to P side, and holes can go from P side to N side, thereby forming what is called the forward current under forward bias. This is the forward bias. So if the forward bias voltage is greater than 0.7 electron 0.7 volt the knee voltage, then you will have forward current. So the energy supplied to these electrons will be sufficient to overcome the potential barrier here, and the electrons from the inside will cross over to the P side and thereby resulting in a forward current. This is the usual IV characteristics, right? So if you consider your forward, if you reduce your forward voltage to 0 here, this is a 0 here, here your forward voltage is 0. If your forward voltage is 0, then the current is also 0. This is the usual IV characteristics. The current is also 0. If you are not applying any external forward biasing voltage, that is VF is 0, your forward current is also 0. So the usual IV characteristics of a PN junction is like this. Now, what happens is that in a solar cell, so in a PN junction, let's say this is a P-type, N-type, and now you shine light on it. You shine light on it. Now, when we shine light on this PN junction solar cell, PN junction cell, and what happens is that when light energy falls on this, like we talked about yesterday, photodiode and all, there will be electron hole pair formation, that is charge carrier generation within the depletion region. When the charge carrier generation takes place within the depletion region, we know that already on the inside there will be positive ions. There are positive ions. Positive ions. Inside of the depletion region there is positive ions. P side there is a negative ions. So when electron hole pairs are formed, before electrons and holes recombine, these positive ions on the inside of the depletion layer will pull the electrons towards the inside. Will pull the electrons towards the inside. Electron hole pair is formed. Electrons will be pulled towards the inside by the positive ions here. And by the negative ions in the depletion region, holes will be pulled towards the p side of the p-n junction. So in this case, what will happen is that there are already majority electrons, there are already majority holes. In addition to the majority electrons and the majority holes, there will be addition of free electrons due to the charge carrier generated by sunlight across the depletion region. So more holes will be generated here because of the charge carrier generated by sunlight. Now, under this condition, if you close a circuit like this, if you connect the circuit like this, electrons will flow in this direction, holes will flow in this direction. You know that conventional flow of current is opposite to the direction of flow of negative charge and same as the direction of flow of current. Therefore, we can say that we will have a current in this direction. We will have a current in this direction. Okay, we will have a current in this direction. Now, if you look at this previous case, when we forward bias a p-n junction in the absence of any sunlight, here we see that electrons are crossing the p potential barrier to the p side, holes are crossing the potential barrier to the n side. So the current direction in this case is like this, clockwise. The current direction in this case is like this because the direction of current is same as the direction of flow of positive charge holes, opposite to the direction of flow of negative charge electrons. So in this p-n junction under forward bias, the direction of current is from p to n. Now, in a clockwise direction, as you see, given by this arrow, as is given by this arrow. Now, if we shine light on the p-n junction, there will be electron hole pair formation after observing solar spectrum. And those electrons and holes, before they could recombine, the electrons and holes will be separated by the potential barrier, that is the positive ions and negative ions here. Electrons pulled towards n side, holes pulled towards p side. So electrons and holes get separated because of this potential barrier, and this will add to the electron accumulation on the n side, hole accumulation on the p side. Now, if you connect the circuit externally using a wire, you will find that the actual current flow is in anti-clockwise direction now. The actual current flow is in anti-clockwise direction, which is opposite to the forward current here. So without any biasing voltage here, you will now be able to have current from the p-n junction. So what happened is that this is the forward current, this is the forward voltage. So this is your usual p-n junction IV characteristics. But when you have a solar cell at zero forward voltage, without any forward voltage, there will be some amount of reverse current here. Okay, there will be some amount of reverse current. So this current, the amount of current that passes through the external circuit, when you just join the p-type and n-type here without connecting any resistance, under no resistance connection, this current is called short circuit current, ISC, short circuit current of a solar cell. Short circuit current. Short circuit in the sense that your n-type and p-type are just joined without any resistance. So now, by now you will be able to see that under light illumination, this p-n junction can now have electrons and electrons accumulation on the n side, holes accumulation on the p side, already there. Those are the majority charge carriers. In addition to that, under light illumination, you are now adding extra electrons on the n side, extra holes on the p side. So your p-n junction cell will now behave like a battery in which you have large number of positive charges in one end and large number of negative charges on the other end. So this is a DC battery, right? In a DC battery, on the bottom side, the negative terminal, you have negative charge accumulated, uh, and on the positive terminal, the top side, in a DC battery, the top side, you will have positive charges accumulated. So negative charges accumulated on one end, positive charges accumulated on one end. Then this is how a DC battery works, right? So if you just join this positive side of the battery with negative side of the battery by conducting wire without any resistance, so this connection in which the positive terminal of the battery and negative terminal of the battery is joined together without any resistance is called short circuit. Okay, so in electrical concept, short circuit means if you just connect the positive terminal and negative terminal of a battery or your household power supply, if you just join, because in every household, in your plug also there are two terminals, right? In some cases there are three pins. So in three pins, the top pin is the earth line, and the two pins on the lower side, one of them is neutral, one of them is phase. So the phase signal is like a positive terminal and neutral is like a negative. So if you just join the positive phase and neutral, then this is a short circuit. So under short circuit, depending on the voltage appearing across those plug, large amount of current can flow through the copper wire connecting the positive and negative terminal, right? So we know that our household power supply is 230 volt peak voltage. So if you just connect the positive and negative of your power plug, then it will just suddenly allow large amount of current to pass through that copper wire, and it will undergo a short circuit condition. When large amount of current passes through it, it will burn the plug, because the amount of current that will flow under 230 volt will be too much. Some large quantities of ampere current, 10-15 ampere current will pass through, and it will probably cause electrical plug damage, and it could cause fire also, isn't it? But like if you just if you just take a small pencil battery, let's say 1.5 volt battery, so if you join them here also, the short circuit current will result in a large amount of current, and it can just damage your battery also if you just connect the positive and negative without any resistance. So just like a battery system, this p-n junction will also function like a DC power source, DC battery source. Okay, so just 1 minute. I need, oh, it's almost over. I don't believe it. I thought we have just begun the class. So another thing which the actual design of a solar cell is like this. Solar cell, in a solar cell, it is not like a normal p-n junction. In solar cell, we usually use a little bit relatively thick, around, this is also not much, around 1 micron, 1 micrometer, that is 10 to the power minus 6 meter, 10 to the power minus 6 meter thick p-type semiconductor will be used usually. P-type semiconductor. And on the bottom of this P-type semiconductor, there will be a metal. You will have a metal here. This is a metal contact. This is called back metal contact. Okay. The back side metal contact. Then you have a P-type semiconductor. And then after that, in the simplest design of a solar cell, there will be a thin N-type semiconductor, relatively thin N-type semiconductor. So this N-type semiconductor is usually around 200 nanometer. Nanometer means 200 into 10 to the power minus 9 meter. Okay, a very thin N-type layer will be used, and on top of this thin N-type layer, there will be another very thin transparent conducting oxide. This is called transparent conducting oxide. Transparent conducting oxide. Transparent conducting oxides, like the material most often used as a transparent conducting oxides is indium tin oxide, ITO2. Okay, indium tin oxide. So indium tin oxide is a conducting material. It's a compound. It's a compound. It is conducting. It is conducting and transparent. But on the back surface, you can use silver or copper, silver or gold, or even copper, silver, gold, copper. They are not transparent. They are metal, means as you know, silver is a metal. It is not transparent. And similarly, gold is also a metal. It is not transparent. Copper is also a metal. It's not transparent, right? So you can use non-transparent back contact metal here, and use a P-type, use an N-type, and then on top of that you have a transparent conducting oxide. So some kind of compound called indium tin oxide is a compound which is conducting, which can conduct electricity and also transparent at the same time. And on top of this ITO, there is this thing called glass, transparent glass. Transparent glass. So transparent, it is covered again with transparent glass to prevent the solar cell from moisture exposure and also damages, like if you put your solar cell on top of your roof, and if a certain bird flies by and then just perch on the solar panel, and it can easily scratch this very thin 200 nanometer N-type semiconductor or 1 micron P-type semiconductor. You can easily scratch those thin semiconductors. But once you cover it with a transparent glass, usually this transparent glass cannot break, so it gives a protection of this p-n junction. Now, what happens is that here in this p-n junction, there is a gain depletion layer here. There is a gain depletion layer here. Now, you shine light on it from the top. So the top surface is covered with glass, as I said. So transparent glass. So this light spectrum, it can easily pass through the transparent glass, and also it can pass through the transparent conducting oxide, TCO or ITO, indium tin oxide. So it will pass through it. Now, as light beam passes through this, it will now arrive at a very thin 200 nanometer N-type. So N-type, we call it the window layer, because it can easily, because of the thinness of this N-type layer, these photons, most of the photons falling on the N-type will pass through it. But some of the photons may be absorbed by this N-type semiconductor also. When it absorbs, it will result in formation of electron hole pair. If the energy of the photon is greater than the band gap energy of your n-type semiconductor, it will result in absorption of photons and formation of electron hole pair. So, but within this n-type here, there is no potential barrier, isn't it? Within this n-type here, like in the case of this, if light falls on this n-type, and when this light energy, photon energy, that is h nu, is greater than the band gap of this n-type semiconductor, this light photon will be absorbed. When light photon is absorbed, electron and hole pair will be formed. But these electron and hole pairs that is formed, they will momentarily be formed and they will momentarily recombine. They will recombine again. Because how do you have electron hole pair formation? Let's say your silicon crystal here. Let's say your arsenic atom, donor atom. Let's say this is silicon. Well, let's say photon of h nu of energy greater than the band gap of silicon. The band gap of silicon is 1.1 electron volt, falls on it. Then this photon will be absorbed, and that will result in breaking of this covalent bond, that is by releasing free electrons from here, and there will be creation of vacancy. Now, this electron hole pair that is formed here will easily recombine. The electrons cannot remain in the excited state as long as it finds a vacancy or empty space. It finds a vacancy or empty space at a lower energy, because we see that the energy state of those electrons here forming the covalent bonding is, we say that this is in the valence band. The energy state of electrons, the free electrons, we say that this is in the conduction band. So it's like by absorption of these photons, if the band gap energy is 1.1 electron volt, if the photon energy h nu is greater than this band gap 1.1 electron volt, electrons will be excited from this valence band to come free electron and holes. And as there is an empty space at the lower energy state, electron will be more comfortable lying in the lowest energy state. Then electron will again falls back and will undergo what the process called recombination. Electron will again participate in the chemical bonding. Right. But when so the electron hole pair formed within this n-type will not be able to contribute to your solar electrical energy. But when light falls on the depletion layer, let's say this is your depletion layer, let's say this is your p-type, thick p-type, let's say this is your thin n-type. When light falls on the depletion layer here, absorption also will result in electron hole pair formation. But we know that in the depletion layer, towards the n side, there is a positive ions. Towards the p side, there is a negative ions. So because of the action of negative ions and the positive ions, that is there is a potential barrier, right? There is an electric field here. So this electric field will easily pull the electrons towards the n side, pulls the electron towards the p side. So